Hi, we are Robocol, and we greet you from Los Andes University in Bogotá, Colombia. We are a team of undergraduate students of 7 different majors who work together for the development of a unique rover. After a year of mechanical, electronic, and software growth, as well as mission simulations and testing, we are pleased to present REMU 2024.
The rover maintains a similar chassis to the previous year, with improved modularity for quick assembly and ease of access, as well as the wheels which have been tested more extensively to ensure optimal traction and allow the next gen of iteration. To improve performance in uneven terrains, we have polished the pulley system to ensure even more reliability and weight optimization. Additionally, new rockers are in the last testing stage, which aims to lower weight and ease assembly. Now we can assemble a rover in 10 minutes.
REMU maintains the same drivers and motors we had last year. However, we have upgraded our electronic box to improve cable and battery management and rebuild our control system, which give us much more fluid control and stability. The optimization of our steering system has increased structural integrity and has reduced power consumption. These improvements now allow REMU to have an autonomy of more than 2 hours with all its gadgets. To improve our battery management, we are for in development of custom-made battery packs that fit our power and size needs, as well as budget and transportation limitations. Our rover is controlled remotely via a ROS2 humble environment, which allows us to achieve reliable communication with the base station and transmit motor power consumption, as well as resetting motor drivers through software. For autonomous navigation, we have implemented a M10Q GNSS and magnetometer, enabling the rover to properly identify its position and distance to the goal. When arriving, the rover scans the area using camera input.
We communicate the pilot with the rover through an architecture deployed on ROS2, allowing us to stream video in real time. Using OpenCV and a trained YOLO V8 PyTorch algorithm, we detect Aruco tags and the required objects in order to guide REMU throughout the autonomous navigation mission.
We've maintained the basis of our communication system, which consists of 2 personalized antennas connected via M2 rockets at 2.4 GHz. For this year, we've implemented Cyclone DDS as our base communication protocol, utilizing a UDP-based architecture for data transmission, which allows us to have low delay control at over 500 meters.
We've maintained the structure of a robotic arm from previous years, utilizing carbon fiber panels as core components and 6-stepper motors for 6 degrees of freedom. The arm features an interchangeable end effector holder. The primary tool is a gripper, which opens and closes flexible pincers. At the heart of the arm lies the electronics box. It has retained the original architecture. However, it underwent significant upgrades last year. This enables us to independently control the speed of each joint and save long trajectories, useful for the equipment servicing mission. This enhancement involves employing 1 microcontroller per motor, synchronized across all 6 motors to ensure movement follows a planned path seamlessly. Movement planning is done via a ROS2 humble environment, which according to the desired relative coordinates and orientation placed on the GUI, checks for collision-free paths, accommodating both general travel and linear motion modes. The interface also provides control over individual motor power consumption, allowing us to boost torque during high-intensity movement, like manipulating heavy objects in the delivery mission, or conserve energy during rest periods. Additionally, a 2D visualizer aids in pre-processing complex tasks, such as drawing, providing the precision needed to replicate shapes like squares and stars on a whiteboard consistently.
To aid the pilot in the equipment servicing mission, we incorporated an OBD camera which uses disparity to accurately process the spatial coordinates of a surface clicked on the screen. This approach allows for a direct integration in the ARM GUI.
The sensory and extraction subsystem uses the EVA and Ramses to retrieve samples to test them and draw conclusions about live detection. Robustness in our onboard lab has been our main priority for this version, now with modular PCBs and a dedicated box to ensure reliability. The Ramses recollects and filters the soil samples and later passes them to the EVA, which distributes them equally inside the onboard laboratory. This last system has 9 compartments incorporated, each one with a different reactant. Furthermore, a camera is installed to observe the reaction results and sensors that give information about particles in the air, humidity, and temperature.
For testing extinct, extant, or no life, the science team uses 5 reagents and 3 sensors that give important information about biological activity, geological history, and habitability. This year, we need the team's training to design better tests, including more specific negative and positive controls of the reagents, which allows us to conduct more in-depth analysis of soil samples. To achieve this, we conducted exhaustive literature research in the astrobiology field, and we also implemented the use of software to explore geology.